Hello there. So I'll talk to you about some new young newcomers to the nanorobot scene. These little guys are like 6 months old, and this is their first public presentation, actually.
Thank you.
And okay. Well, the idea here is to have these little nanobots swim around your body and taking care of your health, delivering drugs and everything. And the picture that I show on this slide, it's quite old actually. It's 96 from a Scientific American nanorobotic illustration concept. And you see that they got little arms and clamps and drills and everything. And it's nearly the same pictures that we see here on the conference poster. That let me tell you that I don't think that's going to happen. We won't have little nanorobots looking like that at all. But there are some major problems that actually have to be solved before we get close to this. The first one is the power source. That if we want them autonomous, we have them to give some power. They have to produce some force so they can move around, they can propel themselves. They have to interact with their environment, so they have to have some sensing capabilities. And if we are talking about drugs and medication and health, so they definitely have to interact with biochemicals inside the body in some ways. Well, external monitoring, Christian has told lots about that, so we have to know approximately where are they. And someday maybe they'll have to communicate with each other or with us. We're looking at them from outside, and maybe someday they'll have some intelligence, but it's quite far away. Anyway, the system that I'm going to talk about has already some of these achieved. Not all together, but well. First, we've got some power source. They can actuate and propel themselves, and they get some basic sensing capabilities. We are actually working on the controlled by mechanical and chemical interactions for these bots. And for external monitoring, we haven't done much yet, but Christian has done, so I put a plus on that for the time being. Actually, I'm a mechanical engineer, so I'll look at the problem from a mechanical engineering point of view. So there's few attempts in the literature to going towards this nanorobot. So the first problem was the actuation and the propulsion mechanism of these guys. So an example was the ATP protein motors was attempted to see if they can drive little mechanism inside the body, but the generated momentum and the power is very weak. So, well, they are odd and beautiful achievements, but not yet for the nanorobotics. There is some work in catalytic propulsion, relying on chemical interactions. I gather that we'll have a talk about that in the afternoon. My personal favorite is Sylvain Martel's magnetic bacteria. I don't know if he's going to talk about that later, but mainly this is the bacteria trained to follow magnetic gradients, and you can drive them inside the liquid, inside a human body, just by modifying a magnetic gradient. And there is similar achievements done later with Marsecan's bacteria, which likes dirt, so you can direct them by using copper ions in the liquid medium. And talking about bacteria, the bacteria's favorite locomotion mechanism is flagella. It has been demonstrated more in millimeter scale in Japan that a rotating flagella was an efficient way to propel things. And afterwards, Bradley Nelson's group in attached set has demonstrated that smaller sizes can work well. But this relies on magnetic actuation. So, for example, they've done a magnetic flagella, which is an HNB, which is roughly the same system that I'm going to talk about. But the actuation, and false holders for small particles, but actuation relies on an external magnetic fields, like in an MRI. Actually, there are two major systems that looks very much like what we're going to do, which are optical and magnetic tweezers. With those systems, you can control a particle, a really small particle inside the liquid medium using a laser beam or using a magnetic field. And when you control the position, and if you get a quite accurate model of what's happening on the particle, you can have an idea of the force that you're applying with this particle. So you have a kind of indirect force measurement with this kind of systems. You've got roughly piconewton force range, and of course you cannot still use them inside the body. You have to use them in under optical microscope. You have to see them. But there's been some quite impressive achievements done with these devices, like unfolding of DNA chains, this kind of stuff. So they have proven very useful. And that's actually what my team started with. We were working on optical and magnetic tweezers, and we decided the next step would be not to use an inert particle that cannot measure anything, but you have to decide, you have to indirectly calculate the force it's applying, and to replace it with something that can actually sense things. And this is how these optical tweezers works. I don't think I need to talk much about that. So this is what our main component. This is the helical nanowells. This is basically a thin film nanostructure. You got two layers. For example, we use gallium arsenide and indium gallium arsenides, but that is not the only solutions. There are other compounds that can be used for that. They are roughly like tens of nanometers thick, and you've got a strain difference between the two materials because of the atomic structures. So when you stick them on each other and when you release them from the substrate, because of this in size constraint, they scroll themselves and they form a 3D structure, a spring-like structure that you see, which is a wonderful surface to volume ratio because the overall thickness is like 20 to 30 nanometers, and we can get them as long as hundreds of micrometers. And of course, at first it was discovered by accident, like 5 or 6 years ago. Now that we understand the system, we can design them to have the exact size and number of turns and dimensions that we want to. And the good thing also in our production process, we can add metal connectors on this. So we can actually electrically interact with these devices. And yeah, I will put them all together. So this is this one that you see, it's one of the first one. It's 70 micrometers long. This model, it's 2 weeks old. It's 20 micrometers long. And I gather that in a couple of weeks, we'll have like 5 micrometer long models coming out. And the production process is quite reliable. We can go for 500 of them in each process, which takes like a half a day, and with close to 95% success rate. So the first good thing about that, like I said, is the sensing. The materials used in the production process, specifically indium gallium arsenide, is piezoresistive. And because of this high surface to volume ratio, they are really, really sensitive. So you can get a very good relationship between the force exerted on this and the current that's modifying. And the equivalent stiffness of the device will be like around 10 power of -3, maybe 4, which is much more better than any cantilever, any AFM cantilever that I don't know if you're familiar with atomic force microscopy. I suppose yes. This is much more better than any piezoresistive cantilever that you can get. And incidentally, if you look at the existing measuring devices and the range of the forces and displacements that's interesting in biomedical applications or biochemical interactions, the helical nanomelt fits the bill very nicely. So that's why we have gone on first on trying to use these components to include in our nanorobots. So okay, we have talked about sensing, and what's the good thing about them? They move. That's the whole point of. Yes. And we have put them inside a liquid solution, isopropyl alcohol in this case, and under an electric field we found out that they move, or if you can modify the gradient of your electric field, they follow the gradient line, so they turn around. So why is this happening?